Assalamualaikum warahmatullahi wabarakatuh. So today our group is going to present on our topic, which is palm oil factory. Assalam. But first, let me introduce our team. We have Ani, Zuhai, Haris Aiman, Irene Maisarah, and me, Safia Jana. There are many types of common work problems in palm oil factories, such as water and soil pollution, waste management, and climate change. These problems happen because of improper management from palm oil factory, and it can harm the environment. So to avoid these problems from happening, we apply 24 hours water supply for palm oil industry.
This diagram represents a fluid distribution system for oil processing, where fluid is transported from a central tank to different sections using pump, pipeline, and valve. The tank serves as the main storage and distribution hub, with pump ensuring a steady flow through the system. Pipeline equipped with control valve for regulation and flow meter for monitoring. Direct the fluid to three key destinations, which is the oil section for storage and further processing, the refining section for purification and separation, and last one, the boiler section for steam generation or heating. This diagram also include 90-degree bands, which indicate change in pipeline direction and may cause minor pressure loss.
So the type of pipe that we use in this design is polyvinyl chloride, which is PVC. It is because of its durability, cost-effective, and versatility. As we know, PVC is much more cheaper compared to other materials. It is able to resist weathering, corrosions, and chemicals, which are very important in palm oil factory. And it also can easily be shaped and molded that can make the engineers easy to design the pipe based on their preference. So the fitting that we use in this design is gate valve and water meter. Gate valve is to control the flow of fluids, either it is liquid or gas. So it is able to either completely stop or allow the flow of a fluid. Basically, gate valve can control the flow by raising or lowering a gate or wedge inside the valve body. Next, the water meter. The water meter is used to measure the flow rate or quantity of a fluid, either it is liquid, gas, or steam, passing through a pipe or conduit. So the water meter is to measure and record the amount of water flowing through a pipeline. The bending that we use in this design is 90-degree elbow. It is used to change the direction of flow in the piping system. It also has several important functions in a pipeline, such as pressure management and connection between pipes. For the pressure management, it can create some resistance and affecting pressure and flow rate. For the connection between pipes, 90-degree elbow can join two pipes at a right angle to form a structured layout.
For pipe sizing and material selection, we choose polyvinyl chloride (PVC) for our pipe material, and we set the diameter of set a 12 inches or 0.30 for 8 meter. Next, for the internal pressure of water distribution network for each outlet, for all attraction, 30 psi, for refining process, 80 psi, and the last one for the boiler system, 100 psi. For the friction factor, dairy waste bag equation. So here is the formula for friction factor. We have calculated the friction factor for each process, and for the oil extraction, the friction factor is 0.02241. For refining process, 0.023286, and for the boiler system, 0.0257.
Assalamualaikum. I am Haris. I am the one who responsible for the oil calculation. So we have to get the velocity first. So for the formula we use that is Q equals to VA. So we have know that the flow rate is 0.00833 meter cube per second equals to V, and the area for this formula is pi d square over 4. So we just put the information that we got and we will get the velocity is equals to 0.1142 meter per second. And then the calculation for Reynolds number RE. As we know, the formula for RE is equals to rho UD over mu, and the density for the water is 997 kilogram per meter cube, and the pipe diameter D is equal to 0.3048 meter. And for the dynamic viscosity, mu, is equal to 0.000891 kilogram per meter cube. And we just put the information and then we got the value for RE is 38,949.20. And for the major loss, the formula is HF equals to F times length over diameter times velocity square over 2g. So for the friction vector, we use the derivative equation, and we will get the value for the friction vector is 0.02241. And we just put all the information together in the HF formula, and we will get the value for the major loss is 0.001466 meter. So now let's move on to the minor loss, which include the bending and fitting in the pipe. So for this pipe, we have bending, which is 90 degree elbow, and also fitting, which is the water meter and gate valve. So firstly, we have to calculate using the minor loss formula, which is equals to K times V square over 2G. So for the gate valve, 75% open, we calculate it and we got the minor loss for the value of the gate valve is 0.000334 meter. And for the 90th elbow, we got the value for the minor loss is 0.000598 And lastly, we have the water meter, and the minor loss for it is 0.004653 meter. And the total loss for all this together, including the bending and fitting, the value is 0.0055836.
Okay, now we will find the value of head loss at the refining process. First, we have to find the velocity. Using the formula, Q equals to velocity time area. And then we rearrange the formula and we get the value of velocity, which is 0.0914 meter per second. With the value of velocity, we can find the value of Reynolds number. Using the formula RE equals to rho VD over mu, we get the value of Reynolds number, which is 31,173. With the value of Reynolds number, we can find the friction factor. In order to find major head loss, we have to use formula HF equals to F friction factor, length over diameter, time, velocity square over 2g. We, subs- we substitute the value of friction factor into the formula and we get 0.000979 meter. This is the value of major head loss. Okay, next we will find the value of minor head loss. In order to find minor head loss, we have to use formula Hm equals to K times V square over 2G. And we get minor head loss at gate valve, which is 0.000161064 meter, and minor head loss at water meter 0.002981 meter. And we sum all the information we get total minor head loss, which is 0.0030x7 meter.
Lastly, for boiler process, we need to calculate the velocity first as we use the formula Q equals to AU, which is flow rate equals to velocity times area. The flow rate that we use for boiler process is 500 liter per minute, but we need to convert it to meter cube per second, and we got 0.005 meter cube per second. And then, as we know, area is equal to pi d square over 4. And the diameter of pipe that we use is 0.3048. So we just need to substitute all of the value in the formula, and then we got the velocity is equal to 0.068 meter per second. Next, we need to calculate the Reynolds number. So formula for Reynolds number is equal to rho ud over mu. The density of water is 1000, diameter is 0.3048 meter, and the dynamic viscosity mu is equal to 0.000891 kilogram per meter cube. So we just substitute all of the value in the formula Reynolds number, and we got the Reynolds number for boiler process is 23362. Next, we need to calculate the major loss HF, and the formula of major loss is friction factor times length over diameter times velocity square over 2g. And we know that the friction factor for boiler process is 0.0257 as we calculate it in the early presentation. And then we just substitute all of the other value in the formula, and we get the major loss of boiler process is 0.000605 meter. Next, we need to calculate minor loss for boiler process. The formula is minor loss equals to K times V square over 2G. K is the coefficient for the bendings and fittings. The bendings and fittings in boiler process are gate valve, 90-degree elbow, and water meter. So for gate valve, the coefficient is 0.25, 90-degree elbow is 0.9, and water meter is 7.0. And then we need to just substitute all the value in the formula, and then we get the answer for minor loss for three of them, which is gate valve is 0.001196 meter, 90-degree elbow is 0.000215 meter, and lastly water meter is 0.00167 meter. And then we need to total up all of the value to know the total of minor loss in boiler process. And then we get the answer is 0.003081 meter. And formula for Bernoulli equation is Hp plus P1 over rho g plus V square over 2g plus Z1 equals to P2 over rho g plus V square over 2g plus Z2 plus theta H major plus theta H minor. We know that P1 is equal to P2, V1 is equal to V2, and there is no elevation because it is horizontal pipe. So we can cancel all of them, and then the last formula we get is HP is equal to theta H major plus theta H minor. So firstly, for all extraction, we know that theta H major is 0.001466 meter plus theta H minor, which is 0.005586 meter. And the total of pressure head is 0.0070496 meter. Next is refining process, which is 0.0009759 meter plus 0.003087 meter. The total is 0.00400629 meter. And lastly, for boiler process, the theta H measure is 0.000605 meter plus 0.003081 meter, which is its delta H minus, and the total is 0.003686 meter. And then we need to total up all of them, all extraction, refining process, and boiler process, and the answer is 0.01478985 meter.
So now, let's look into why our pumps are essential components of water distribution systems. Firstly, for pressure boosting, pumps help maintain adequate pressure throughout the distribution system, especially in areas with varying elevation or long distance from the water source. Without pumps, water might not reach the farthest or highest point effectively. Secondly, for continuous flow, pumps ensure a consistent and reliable flow of water to meet the demand, whether it's for residential, industrial, or agriculture use. Thirdly, for overcoming elevation differences in system where water must be delivered to elevated areas like high-rise buildings or hilly terrains, pumps provide the necessary energy to lift water against gravity. What purpose do pumps serve in the context of water distribution networks? It consists of three, which is balancing supply and demand. Pump work to maintain a steady supply of water across the system. Secondly, boosting water pressure. Boosting water pressure, which pump ensure adequate water pressure is maintained throughout the system. And lastly, transporting water over long distance. Pump facilitate the movement of water from sources or tank to the system. How do pumps facilitate the movement of water within a distribution system? Firstly, by providing pressure for motor movement. Pumps generate the pressure needed to push water through pipelines, ensuring it reaches distant or elevated location. They counteract losses due to friction in pipes and overcome gravity when lifting water to higher elevation. Secondly, by regulating pressure and preventing backflow. Pressure regulating pumps help maintain optimal pressure levels, preventing pipe damage and leakage. Some pumps also prevent backflow, ensuring water moves in the desired direction. Lastly, maintaining flow and supply. In large distribution networks, booster pumps help maintain steady water flow and pressure across long distance. They ensure that water is evenly distributed even in areas with high demand. What considerations should be considered when selecting the appropriate type of pump for a distribution system? Firstly, we have system design and layout. It consists of pipe diameter and length, and also pipe material and fittings. Next, elevation and distance differences. Pumps must be selected based on whether they need to lift water to elevated tanks or push it over long distances.
For the comparison of different type of pump efficiency in terms of its performance curve, pump cavitation, and also NPSH requirement. Centrifugal and positive replacement pump different in their performance curve, cavitation risk, and NPSH requirement. Centrifugal pump follow a parabolic performance curve where efficiency peaks at the best efficiency point BEP and decline afterward, while positive replacement pump provide stable and linear flow regardless of pressure change. In terms of cavitation risk, centrifugal pumps are more prone to cavitation if the net positive suction head is insufficient, leading to noise, vibration, and potential impeller damage, whereas positive replacement pumps have a lower cavitation risk but can experience vapor lock. Additionally, centrifugal pumps require higher NPSH as flow rate increase, making it essential to design the system so that the available NPSH is greater than the required NPSH. In contrast, positive replacement pumps have lower NPSH requirement, making them ideal for handling high viscosity fluid.
Okay, we choose a centrifugal pump as our pump. A centrifugal pump is one of the simplest pieces of equipment in any process plant. And this is a working principle of a centrifugal pump. Liquid is forced into an impeller either by atmospheric pressure. The vents of impeller pass kinetic energy to the liquid, thereby causing the liquid to rotate. The liquid leaves the impeller at high velocity. The impeller is surrounded by a volute casing, or in the case of a turbine pump, a stationary diffuser ring. The volute of or stationary diffuser ring converts the kinetic energy into pressure energy.
Now, we will be discussing about the safety and environmental consideration in a water distribution system. So, we have to take these two safety measures to increase the safety in the industry setting. The first one, we have surge protection device, water hammer. A surge arrestor absorbs the excess pressure, preventing pipe failure and costly downtime. The second one, pressure relief valve, PRVS. PRVS prevent excessive pressure build-up by automatically releasing excess pressure when it reaches the dangerous levels. This helps avoid pipe bursts, equipment damage, and explosions. For the environmental benefits, it enhances process efficiency and sustainable operation. By maintaining consistent pressure and flow rates, industrial processes become more resource efficient, leading to lower waste production and higher sustainability. Secondly, lower energy consumption and carbon emission. Industrial pumps, compressor, and boiler work harder when dealing with pressure fluctuation, consuming more energy than necessary. Stabilizing pressure reduces excessive power use, leading to lower carbon dioxide emission. Lastly, reduce resource waste. Uncontrolled pressure surge can cause leaks, pipe bursts, and material loss, leading to waste water, fuel, and raw material. PRVS and surge protection device optimize flow control, reducing unnecessary loss.
For energy efficient pumping practices, first we use proper pump sizing and system design, avoiding oversized pumps which often operate inefficiently. Second, we use high efficiency pumps. We will select pumps with high hydraulic efficiency to reduce energy use. And third, we use variable frequency drives. Adjust pump speed based on demand to reducing energy wastage. And next, impact on energy consumption. First, for proper pump sizing, it will prevent excessive electricity usage. And second, high efficiency pumps. Do you know all the pumps operate at 50 until 60% efficiency, leading to high energy losses? So, with high efficiency pumps, 80 until 90% efficiency require less power for same input. And third, using variable frequency drivers, VFD control pumps adjust speed based on real-time demand, reducing power consumption. Next, operational cost. With a proper pump sizing, right sizing pumps based on peak and average water demand prevents excessive electricity usage. And second, high efficiency pumps. Optimized pump performance lowers electricity bills by reducing idle power consumption. And third, using variable frequency drivers. A centrifugal pump with VFD can achieve 30 until 50% energy savings compared to a fixed speed pump. Next, for engaging stakeholders and foster culture awareness. First, internal stakeholder engagement. We will training for operators and engineers. And then we will do incentive programs, which such as we will reward staff for ideas that improve water efficiency or reduce energy waste in factory operations. And next, external stakeholder engagement. First, we will do collaboration with supplier for sustainable equipment. And second, community awareness. We will spread awareness at community in that area. And then lastly, challenges in implementing sustainable water practices. First, high initial cost for upgrades, which is difficult funding pump upgrades. Second, resistant to change, which is operators prefer existing method. And then lastly, infrastructure constraint, which is pipelines, inefficient pumps, and shutdown risks.